Hello, my name is Rob Reynolds. Welcome to Mat-073. Today we're looking at section 4.6. We've been studying factoring techniques, and today we look at some special factoring types of problems, factoring trinomials, the difference of two squares, factor by grouping, and factoring cubes. Now, if you haven't looked at section 4.4 and 4.5, I'd go back and look at the greatest common factor. That's the first technique that we learned, and that's what you always want to try to look for first. And then I've also looked at a couple of section 4.4 and 4.5 talked about factoring by trinomial. So you want to definitely look at those videos before you look at this video. All right, so here we go. We learned how to factor trinomials before by looking at factors of 16 that add up to 8. So we know that 4 and 4 are factors of 16 and they add up to 8. Signs are alike. They're both positive. But notice that even though this is the answer, we can simplify that, and it's called a trinomial square. So this is a perfect trinomial square because you can write it as a binomial square. So a perfect trinomial square means you could write it as a binomial times a binomial times itself. Why that's important, I'm not 100% sure, but it's a special type of factoring. And really this is more simplified because this is easier to solve for when it comes to those terms. So to recognize those terms, we're looking for the A term and the B term to be perfect squares. So here's your A and here's your B. So 1 is a perfect square and 16 is a perfect square. And so let's see if we can recognize it a little bit better. So be careful. This does not equal, this is the mistake that students always want to make, A squared plus B squared. So you can't distribute those exponents over addition. This actually equals, if you do the FOIL methods, square the first, it's twice the product, square the last. Same thing for subtraction. So look at this, perfect square could be a binomial square. So I'll try 5 and 5, and sure enough, factors of 25 that add up to 10 are 5 and 5. Signs are alike, they're both positive, and so we'll write this final answer as n plus 5 quantity squared. And that's what the author has as well. So again, we're looking for perfect binomial squares, and I don't quite have it here until I remember that first lesson, always look for the greatest common factor first. So let's pull out a 5, or factor out of 5, which literally means divide each term by 5, giving me x squared minus 2xy plus y squared. And look at this. This is a perfect binomial because I got 1's in front. So what are, the only thing that gives me an x squared is an x and an x. The only thing that gives me y squared is a y and a y. And signs are alike. They're both negatives, if you watch the previous video. And you can write this as 5 times x minus y quantity squared. And again, that's what the author gets. So the difference of two squares looks a little bit different. So before we were looking at perfect binomial squares, and so that looked like a plus b, the whole quantity squared. Now we're looking at a squared, so don't get that mixed up. So a minus b quantity squared does not equal a squared minus b squared. So we come up with different rules. This is called the difference of two squares over here, and this is that perfect trinomial squared. So let's look at this. I need factors. Let's see. This is x squared, and this is really 7 squared. So both terms are perfectly squared, but I have no middle term this time. So the rule states I'm going to say x plus 7 and x minus 7. Is for the final answer. You can FOIL that back together, and the neat part is it's called the conjugate. The outer terms and the inner terms will cancel because this is a negative 7x and this is a positive 7x, which gives you no x term in the middle. So it's called the difference of two squares. Sure enough, the author agrees. So one more example. Before you try the difference of two squares, always look for the greatest common factor. In this case, I think I can pull out a 3, and oh, look at this. I also have an n squared. So let's pull out a 3n squared, which literally means divide each term by 3n squared. If you need to write this red step, you're certainly welcome to, but you're really kind of just thinking about what's happening to this term after you divide by 3n squared. And I think I have an n left. Actually, I have 2 n's left because there's 4 n's up here, minus, let's see, that's 27 divided by 3 is 9, and the n squareds cancel. So you might think that you're done, but all we've done is the greatest common factor. You can also always, whenever it says factor, it implies factor completely. So I would not accept this answer because I think this is a perfect square and this is a perfect square. So of course 3 and 3 gives you the 9, and mn times mn will give me that first term. So this is again called the difference of two squares. This is signs are going to be different. One's a plus, one's a minus. And I think that's the final solution that we're looking for. And the author agrees with me. So sometimes when factoring a polynomial, when you find four terms, you want to factor by grouping. So we're going to oftentimes group the first two terms together and the last two terms, although that's not always the technique. I'll show you an example in a moment. But let's try that. If I group the first two terms together, the GCF here is y to the fourth, leaving you with y squared minus 9. Now the trick here is if you really did factor by grouping successfully, you've got to get another y squared minus 9. Otherwise, we got to try different factoring techniques like synthetic division, which I haven't even taught you yet. So what number goes in here times the y squared that will give me this 2y squared, and of course that number's got to be a 2. But the check it. Does 2 times the negative 9 give me the negative 18? And the answer is yes. So I think I've successfully got the same term. This y squared minus 9 and y squared minus 9 can actually be factored out here. So I'm going to pull out a y squared minus 9 term. And again, remember, literally that means divide each term by y squared minus 9. You don't need to write the red step, but that's actually what's happening. You're canceling that out. So the only thing that's left is the y to the fourth. Oh, how about a positive 2 in here? Because positive 2, this gives me this positive term. So plus 2. Uh-oh, we're not done. This yellow term, I see, remember it says factor, but it implies factor completely. I think this is the difference of two squares. So y plus 3 and y minus 3. And y to the fourth plus 2. And remember, you can multiply in any order. So the author may have this in a little bit different order. Sure enough, he stuck the highest degree first. But I would accept any one of those answers. So let's try this factor by grouping again here. Uh-oh, I don't see any GCF of the first two terms. So you may want to consider trying to reorder using the commutative property before you start trying to factor by grouping. So sometimes this is necessary. Let's see what we can do. Let's put the x terms together. Now I've got a couple x terms. I'm going to try the x squared plus 2xy. If this doesn't work, I would have put the negative 3z, but let's just try this first. And the reason why I did that is because I see I have a z term here and a z term here, and I thought maybe it would be nice to stick the z terms together as well. So let's see. The GCF of the first two terms is x, leaving me with x plus 2y. Now remember, the trick here is I like to just immediately write down another x plus 2y. And if you can't get this x plus 2y, then we need to reorder or rethink about how to factor this using other techniques, which again is called synthetic division, which I haven't even taught to you yet. But let's just see. What number goes here times this x that gives me this guy? Because that's what I'm for next. So let's see. I don't have anything. So I wonder if I should throw these two terms around. So let's put the negative term first. So let's put the negative 3xz term first, and then followed by the negative 6yz, and ask the exact same question as we did before. What number goes here now times x that gives me this guy? And that's a negative 3z. Now, if this negative 3z times this 2y doesn't give me this last term, then I need to try something else. So negative 3z times the 2y, sure enough, gives me that negative 6y, and I'm home free. Hopefully this will work for you for all the problems in this section, because I haven't taught you any other techniques. So keep trying to play around until you can get that common factor. And in this case, the common factor is the x plus 2y and x plus 2y. So I'm going to factor out that x plus 2y. So let's see, x plus 2y, and that leaves me, again, that literally is thinking about dividing out x plus 2y, leaving me with x minus 3z. And then, of course, I always look for, can you factor some more? And I don't think so. So again, final solution here. So again, to recap a couple things, we can factor trinomials, we can factor the difference of two squares like x squared minus 9. But remember, you cannot factor the sum of two squares. So this factors to x plus 3, x minus 3. But it's always strange when students start thinking that x squared plus 9 can be factored to, oh, maybe they think x plus 3 and x plus 3, which is simply not true. This actually equals x plus 3 quantity squared, which we've already learned is that perfect trinomial squared, plus square the first, twice the product, square the last. So don't get this mixed up with this. They're not equal. So you cannot factor the sum of the sum of two squares, but you can factor the sum of two cubes. So that's what we're going to look at here. The sum and the difference of two cubes comes next. But again, I'll have a sad face if you try to factor the sum of two squares. It can't be factored, so don't fall down to that trap. So here's how the book teaches the rules for factoring sums of two cubes, and this is what I do down here. So I'm going to start saying, write down the bases, square the first, take the product, square the last. First you keep it, then you change it, last one's always plus. What that means, I'm going to explain right now. I think that's easier than just following through. But the base is an A, so that's write down the bases. That's the A and the B. You square the first, take the product, square the last. First you keep the sign, and that's a plus, so here's you keep it. Then you change it, so here's the change, and the last one is always plus. So those are the rules written out in words for you. So here we go. Following these rules, write down the bases. You might want to think about the x being a base, and then 8 is not the base, but 2 is the base, because 2 cubed is 8. So if I were to ask what are the bases, I would stick with x is a base and 2 is a base. So when I say write down the bases, I'm talking about just that. X is a base and 2 is a base. Now the trick is, don't put the signs in until last. First you keep the sign, then you change the sign, and the last one's always plus. We'll worry about that in a moment, because I don't want you to worry about any of the signs yet. So it says, square the first base. So don't look up here anymore. Look down here. So the first base is x squared. First you square the base. Then you take the, you square the first. Now we're taking the product. So the product of the bases, well, the first base is x. The second base is a 2, so it says take the product, so that's just 2x. Square the last base, which is a 4, and then step 5 says first you keep it. Well, what the heck is it? It is the sign from the original problem. So it is, first you keep the minus, then you change it, the last one's always plus. So that's how you factor cubes. And the author agrees. Let's try one more. This looks like it can be factored because I could rewrite b to the 6th as something cubed, and I think it's a 2, because b squared cubed, power raised to a power, is the 6th. The other base is, well, I think 5 cubed is 125, and I need a y there too, because 5y times 5y times 5y is this big. So the trick is to write these things in terms of being cubed. So when I start asking for bases, then it's obvious that the base is b squared and 5y. And that's what I start with, those bases. So here we go. Let's write down the bases, as we've already identified. B squared is the first base. 5y is the second base. The rule states, square the first. So b squared times b squared is b to the 4th. Take the product, so it's going to be 5b squared y. Square the last, 25y squared. First you keep it. It's a plus. Keep it right here. Then you change it. The last one's always plus. And then you always want to see if you could factor some more, which I really don't think we can. So here's how the author chose to do that. So again, the directions here are going to say factoring. We want to pull out a GCF, which I think is 2m squared. Literally what's happening is you're dividing each term by 2m squared. That's called the greatest common factor. So what's left is m cubed plus, and don't forget about this 1. Any number divided by itself is a 1. Now, whenever it says factor, it always means factor completely. So you might think that you're done because you factored out the greatest common factor, but I think I see a sum of cubes here. M is being cubed, and don't forget that 1 cubed is 1. So I've got a base of m, I've got a base, so when I say write down the bases, you write down m and 1. Now don't look up here, we'll just look down here. It says square the first, take the product of m times 1, square the last. First you keep it, it was a plus, then you change it, the last one's always plus, and I think I'm done. We'll see if the author agrees. Yes. So that's how to factor by cubes. We've learned a lot today. We can factor sum and differences of cubes. We can only factor the difference of squares. Don't fall into the trap of trying to factor the sum of two squares. X squared plus 9 is actually prime. I can't factor that. I hope this video was helpful. If you have questions, feel free to email me. Have a good day.